Hello everyone, I am Dr. Rashmi Roy. I am working in Madanapalle Institute of Technology and Sciences in the Department of Chemistry. So today I will deliver a lecture on pericyclic reaction, and I am going to deliver a series of lecture on this topic. And today it will be my first lecture. And first I will introduce myself, and then I will come to the topic. So I am Dr. Rashmi Roy. I did my PhD from IIT Kanpur, and after that I moved for a postdoc. And after returning to India, I worked in three industries: Integral Biosciences Private Limited, Noida; GVK Biosciences, Hyderabad; and TCG Life Sciences, Kolkata. Then in 2024, I have joined here in Madanapalle Institute of Technology and Sciences in the Department of Chemistry as an assistant professor. So today, first we will discuss about what is a pericyclic reaction. Then we will discuss about types of pericyclic reaction. What are dienes and dinophiles in Diels-Alder reaction? And now coming to the point, the ISIS criteria of dienes in Diels-Alder reaction. Next, I am going to discuss about frontier molecular orbital approach of bond formation and Woodward-Hoffman rule. And lastly, I will discuss about the endoselectivity in Diels-Alder reaction. And that's all about today's presentation. So, most of the organic reactions are ionic in nature. Electrons move from an electron-rich species towards an electron-deficient species, and anions and cations are the intermediate. For example, if we take account of the cyclic ester formation, the reaction goes through following steps. Uh, the the reaction is acid catalyzed, and first this acidic group is protonated in presence of acid catalyst, and then intramolecular attack of this hydroxyl group will take place here to form a cyclic oxonium ion. And from this molecule, one water molecule will liberate, and the molecule will undergo tautomerization to form the desired lactone. This reaction goes through 5 steps and 4 intermediates, and the reaction is catalyzed by acid, and each intermediate is ionic in nature. Here, electrons are flowing towards the positive charge, and this is an ionic reaction. In this lecture, we will discuss about a totally different kind of reaction. Here, electrons move in a closed circle, and there are no intermediates formed. In intermediates, that means ions, free radicals, etc., does not form during the course of the reaction. All the reactions are concerted and they goes through a cyclic transition state. So all such concerted reactions which proceed via cyclic transition state is known as pericyclic reactions. Now there are four kind of pericyclic reactions. One is cycloaddition, second one is electrocyclic, third one is sigmatropic, and fourth one is geletropic. So today we will discuss mainly about cycloaddition reactions. The other reactions I will cover in my next lectures. So cycloaddition reactions could be subdivided into three categories: 4n plus 2, depending upon the number of pi electrons taking part in the reaction. So first one is 4 plus 2 pi electron cycloaddition reaction. Next is 2 plus 2 pi electron cycloaddition reactions. And the third category is 3 plus 2 pi electron cycloaddition reactions. This is also known as 1,3 dipolar cycloaddition reactions. So first, coming to the point, so first I am going to discuss about the 4 plus 2 pi electron cycloaddition reactions. I am going to discuss these reactions both in thermal mode of activation and also in photochemical mode of activation. So, thermal 4 plus 2 pi electron cycloaddition reactions are also known as Diels-Alder reaction. And Diels-Alder reaction is the one for addition of, of an unsaturated molecule with a conjugated diene to form a six-membered ring. And in Diels-Alder reaction, scene addition takes place, and the reaction involves the shift of 4 pi electrons of the diene and 2 pi electrons of dienophile. Now, what are these? Now, I'm going to discuss about the examples of these dienes and dienophiles. But dienophile, simple monoene without substitution, makes a poor dienophile in Diels-Alder reaction. When some electron withdrawing group is attached to to this monoene, it makes a good dienophile for Diels-Alder reaction. Here are the examples of such dienophiles. Here we can see that ester group, an aldehyde group, cyano, nitro, etc. These when these electron withdrawing groups are attached to this monoene, it acts as a good dienophile. And also maleic anhydride and benzoquinone. These are two classic example of dienophiles in Diels-Alder reaction. There are these molecules can also act as a good dienophile, shown here in Diels-Alder reaction. Now, what are the examples of dienes? Dienes may be a conjugated diene or polyene or enine or dienes. An aromatic compound can also act as a diene. But in that case, at least 3 rings has to be fused together, like in case of anthracene. Here, Diels-Alder reaction takes place through its 9 and 10 position. And another thing is that when an electron releasing group is attached to this diene, it makes a good diene for Diels-Alder reaction. Now I will discuss about the ACEs criteria of diene for a successful Diels-Alder reaction. So what are ACEs and trans dienes in Diels-Alder reaction? When two double bonds of a diene orient themselves in the same direction of carbon-carbon double bond, in that case they are called as ACEs diene. It is shown here. And when these double bonds orient themselves in opposite directions, in that case, they makes a S-trans diene. Here it is shown here, it is S-trans. So it is to be noted that the diene part of the Diels-Alder reaction component must react in its S-cis conformation. If steric interaction hindered the molecule to assume a cis conformation, then Diels-Alder reaction does not take place. For example, here in these two molecules, methyl-methyl steric interactions, and here CMe3 steric interaction takes place, and it forces the molecule to orient themselves in S-trans conformation. So these molecules do not undergo Diels-Alder reaction. Now coming to these two molecules, here the molecules locked themselves in S-trans conformation, so they cannot undergo Diels-Alder reaction. And here this is an example of linear sp hybridized molecule, and it never can assume the cis conformation, so it does not undergo Diels-Alder reaction. Now I am going to discuss about some classic examples of Diels-Alder reactions. First example is our reactions with cyclopentadiene. Now this is the dimer of cyclopentadiene, and when this molecule is heated, it gives cyclopentadiene. When this cyclopentadiene reacts with chlorine molecule, it gives perchlorinated cyclopentadiene. When this perchlorocyclopentadiene reacts with maleic anhydride, it gives this Kg molecule. And this is a complicated molecule and could be synthesized in a single step through this Diels-Alder reaction. This molecule is a flame retardant. Now coming to the second example, here 2,3-dimethyl butadiene reacts with this alpha beta unsaturated carbonyl compound at 100 degrees Celsius to form this 6-membered ring system. And by this way, we can synthesize 6-membered ring in a single step using Diels-Alder reaction. Now I will discuss about the formation of two pesticides, olrine and dialdrine. So this is the structure of the pesticide olrine, and dialdrine is the simple but the epoxide of this olrine molecule. And this olrine could be synthesized by two successive Diels-Alder reactions, which I am going to discuss here. Uh, so first cyclopentadiene reacts with acetylene to form this symmetrical cage molecule norbornadiene. It is also known as bicyclo-221 heptadiene. Now, norbornadiene is not a conjugated system, and it cannot take part in a Diels-Alder reaction as a diene, but it can act as a good dienophile. So now this norbornadiene reacts with perchlorocyclopentadiene to form this aldane in a single step. So by utilizing this Diels-Alder reaction, we can get complicated molecular frameworks in a single step, which is not possible by means of other reactions. Now, these tetracyclic molecules has been synthesized using Diels-Alder reaction in a single step. You see here, this is a diene and benzoquinone is a dienophile. Here, it undergoes Diels-Alder reaction to form this tetracyclic molecule in a single step. And lastly, I am going to discuss about reaction between cyclopentadiene and nitroolefin. Here, cyclopentadiene reacts with nitroolefin to form this bicyclo-221 heptane cage in a single step. So now we can understand how important is our Diels-Alder reaction is. Such complicated molecular frameworks would be synthesized in a single step by using this 4+2 thermal cycloaddition reactions. So now I am going to discuss about the molecular orbital interactions present in this cycloaddition reactions. So before going to that topic, we have to understand the molecular orbital of 1,3-butadiene and ethylene system. Now, butadiene contains 4p atomic orbitals and 4 pi electrons. Now, these 4p atomic orbitals combine themselves to form 4 molecular orbitals. These molecular orbitals are shown here. This Chi1, Chi2, Chi3 star and Chi4 stars are 4 molecular orbital of butadiene system. Now, among them, Chi1 and Chi2 are bonding molecular orbital and Chi3 star and Chi4 star are antibonding molecular orbitals. And as we go from Chi1 to Chi4 star, number of nodes will increase one by one. The Chi1 contains no nodes and Chi4 star contains 3 nodes. Now, butadiene system has 4 pi electrons. Among them, 2 pi electron goes to Chi1 molecular orbital and another 2 fills the Chi2 molecular orbitals. So, for butadiene system, Chi2 is our highest occupied molecular orbital or HOMO, and Chi3 star is the lowest unoccupied molecular orbital or LUMO. And for ethylene system, in ethylene, we have 2 pi electrons and 2p atomic orbitals. These 2p atomic orbitals combine themselves to form one bonding orbital that is denoted as Chi1, and another is antibonding orbital that is denoted as Chi2 star. So, and these 2 pi electrons fills Chi1 molecular orbital. So, for ethylene system, Chi1 is our highest occupied molecular orbital and Chi2 star is our lowest unoccupied molecular orbital. When this Diels-Alder reaction takes place, that means when 4n plus 2 thermal cycloaddition takes place, what happens? HOMO of diene interacts with LUMO of ene. So here HOMO-LUMO interactions is shown here. Here orbital overlap is taking place in supra-supra manner. That means in same side of the orbital overlap together to give bonding interaction. Um, According to frontier molecular approach, HOMO of diene reacts with LUMO of ene to give bonding interaction in cycloaddition reaction. Now, what happens when LUMO of diene reacts with HOMO of ene? In that case, also bonding interaction takes place supra-supra manner, but LUMO of diene and HOMO of ene has higher energy difference, that is 11.5 electron volt, than that of HOMO of diene and LUMO of ene, that has lower energy difference, that is 10.6 electron volt. So most of the Diels-Alder reaction goes through the interaction of HOMO of diene and LUMO of ene. Now here one thing we have to consider, that when electron releasing groups are attached to the diene and electron withdrawing groups are attached to the dienophile, in those cases reactions are more facile in Diels-Alder reaction. Those things I will discuss later in my future videos. So today I am not discussing it much details. Thus just only we will understand that HOMO of diene reacts with LUMO of in to give a proper combination in Diels-Alder reaction. Now, if we consider 4n plus 2 pi electron cyclization reaction in photochemical mode, then what happens? You see, this is our molecular orbital diagram, and this is our HOMO when we consider thermal mode of activation. In case of photochemical activation, what happens? One of the electron from HOMO jumps to the psi 3 star. Now, psi 3 star becomes HOMO pi star in this 1,3 butadiene system when mode of activation is photochemical. Now, you see, this is our HOMO pi star. Now this homopister of this diene reacts with LUMO of in, and in that case, if we consider supra-supra overlap, orbital symmetry does not match and bonding interaction does not take place. So most of the 4n plus 2 pi cycloaddition reactions does not take place in photochemical mode. They only take these reactions goes via prefer to go through thermal mode of activation, that is Diels-Alder reaction. Now I will discuss about the 2 plus 2 pi electron cycloaddition reactions. How orbital interactions take place in 2 plus 2 pi electron cycloaddition in thermal mode. In thermal mode, one of HOMO of one in reacts with LUMO of the other in system, and here this HOMO-LUMO interaction does not give bonding interaction if we consider supra-supra mode of overlap. But supra-entera mode is symmetry allowed. But thing is that this supra-entera mode of interaction is not geometrically favorable. It is, and so this interaction does not give to a bonding overlap. So 2 plus 2 pi electron cycloaddition in thermal mode does not take place at all. But 2 plus 2 pi electron cycloaddition in photochemical mode, when we consider this photochemical mode of interaction, then this HOMO pi orbital of our in system under photochemical activation converted to HOMO pi star system. Now this HOMO pi star overlaps with LUMO of the other in system and gives a nice bonding interaction if we consider supra-supra mode of overlap. Here it is shown here, and by using this reaction we can make cyclic four-membered systems, and which are strange systems and are very difficult to make, but they could be synthesized by 2 plus 2 pi electron cycloaddition in photochemical mode. So based on these above molecular orbital interactions, Woodward and Hoffman generalized the following rules for cycloaddition reactions. If our number of pi electrons involved in the reaction is 4n, that is 2 plus 2 pi cycloaddition reaction, and our mode of activation is thermal, then allowed stereochemistry is supra-entera. And if the mode of activation is photochemical, then allowed stereochemistry is supra-supra. But we all know that supra-entera interaction is geometrically difficult and supra-supra interactions are geometrically favorable. So most of the 4n cycloaddition reactions goes through photochemical mode of activations only. And if we consider 4n plus 2 pi electron cycloaddition reactions, when mode of activation is thermal, allowed stereochemistry is supra-supra, and when mode of activation is photochemical, our allowed stereochemistry is supra-entera. And since supra-supra interaction is geometrically favorable, so most of the 4n plus 2 thermal the cycloaddition reaction goes via supra-supra mode of overlap only, and that means 4n plus 2 thermal 4n plus 2 cycloadditions goes via thermal mode of activations only. Now, lastly, I will discuss about the endoselectivity of Diels-Alder reaction. In Diels-Alder reactions, there are possibility of two product formations. One is exoadduct, that is thermodynamically more stable, and one is endoadduct, that is kinetically controlled product. And this extra product is free from any kind of steric interactions, and it is thermodynamically stable. And that is why we can expect that during the course of the reaction, our extra product will be the major product. But in reality, it is found that our endoadduct is the more is producing in more amount in Diels-Alder reaction. We can explain this incident in by considering the orbital overlap interactions of dienes and dienophiles. You see, this is the orbital overlapping interactions taking place for the case of exoproduct formation. Here, only homo of diene is reacting with lumo of dienophile. Only this homo-lumo interactions present here, and molecule is free from any kind of your steric interaction. And this is the formation of our endoadduct. Here, along with these homo-lumo interactions, many secondary orbital overlaps are also taking place from the backside of the molecule, and it gives an extra stability to the molecule. So, although steric interactions present in case of endoadduct, the secondary orbital overlap overweighs these steric interactions, and that is why we get this product in major amount during the Diels-Alder reaction. So, in summary, we have discussed about a new kind of reaction, that is pericyclic reaction, and how many types of pericyclic reactions are there. We come to know about the Asst's rule of diene, an essential criteria for Diels-Alder reaction. We have discussed about the frontier molecular orbital approach of bond formation in cycloaddition reactions and Woodward-Hoffman rule. And we have also discussed some classic examples of Diels-Alder reactions, and lastly, we have discussed about the endoselectivity in Diels-Alder reaction. So, I am going to finish my lecture here itself. The most of the contents I have taken by consulting these two books. One is Clayden's Organic Chemistry, and another is Subrata Sengupta's Basic Stereochemistry of Organic Molecules. If you want to discuss, if you want to know more about these reactions, you can consult these books. And if you have any comments or queries regarding this lecture, you can post comment in the comment box. And thank you for your time to listen to this lecture. Bye bye, everyone. Thank you.